forgot. I keep forgetting. All right. So far, you learned how to represent a system in time domain, in S domain, to move between them. What are the important characteristics of the system in each of these domains? You know how pole and zero impact the system, right? You work with transfer function, you know how to deal with steady state error, and what type of system can handle what kind of input to give us error of the steady state error of 0 or a constant value, or they would not track. You know how to evaluate the system to see if it rejects a disturbance and if it can track an input. Meaning that if we have a desired value, can our system track it and get to that desired value? That's what tracking means, right? So tracking is usually you have input to your system. You want to know if your system follows it. Rejection is that you have disturbance and you want to make sure your steady state error is either 0 or very minimal due to that disturbance, correct? So that was the summary of what happened so far. Now, to do all of that, when we are trying to change the behavior of our system, we are designing a controller, okay? Now, if you remember from our last examples, there is no one set value for controllers, right? Controllers have gain, you can choose a value between a subset, okay? That's what makes designing a controller interesting, because you can always find values that, it's 3:07. You managed to be later than me. All 4 of you. Okay. I can't tell who does homework with who. It's funny. All right. So what does controllers do based on all the things that you have learned so far? That's the part we talk. Skip the first row because they are brave to be on the first row. They control things. Great. Now let's say you have a system that has a behavior, right? Now talk about that. Because we are in control class, right? So we want to talk more systematically, like from system point of view. Drew. No, you can keep your mask off. I don't care at this point. What does the controller do? Yes, because today or 4 days from now, I don't understand. Don't report me. I'll make you wear a double mask. Okay. To certain, what is that certain value? Correct, but I want you to explain it better. Yes, right. So when you have a system that has a behavior, right? And you have a desired behavior of a system. When the system does not act as you desired, you want to control it, right? You want to change the behavior of the system. Make sense? So every time you're designing a controller, your first question should be, how's my system behaving? Right? So how's your system behaving? Is it what I desire? Yes, leave it alone. If it's not what I want, then I'm going to manipulate it and change it in a way that it does. So that's your controller, right? We call it controls things. Now, it could be, you could call it compensator, is the same thing. Compensating for a lack of something in your system. Yes.
So like with all the concepts that we've used, are very like I understand like the math and the tools behind it, but like how do you take like say I'm like my iPad, how do you take that and be like I'm gonna get this system?
So do you remember when we defined system? So your iPad is a very big system, devising subsystem. You have to exactly say what system, what subsystem you're trying to control. What's the output of that? What do you want that output to be? So if it's a transistor in there that you want that needs to do something specific, then you need to control the output of that. So iPad as a whole is a very big system. You will have like tons of controller inside. So you have to define that subsystem. So it's very important to know what is the system you're trying to control. All right. That's a subsystem of it.
What would
Right.
be like the measure? Like, I know we talked about like, the time, but you
Good.
said all.
Yeah, I can answer that. Let's leave it after lecture because I need to finish this, but I have the answer to your question. It's actually good. It's very simple. Control it. All right, so let's say you all know Wall-E. Yes, their favorite, my favorite, right? No, get out. So let's say this robot wants to go on a straight line, right? It has wheels, so it's in the wheel category. Wants to start from here and then go on a straight line. So from a start, goes to this direction is desired. It's the desired path, right? It's called the path. And then it's going along an axis or in direction. This is the x direction. Okay. So if everything works, everything is aligned, this robot will go on the straight line, right? Now, due to the error of the system, whatever error or the environment, if there is a bump on the road or there's something wrong with the subsystem in there, for example, the wheel, this robot might get off the track and end up here, right? This would be the final position. Stop there. The robot thought is going 3 meters straight. The controller, like the brain, sent that measure, but it ended up having some error, right? This is error in position, agree? So wanted to go on X direction straight, it had an error that also went on a curve instead of going on a straight line. So there are two problems here. This robot went on a curved path instead of a straight path and has a direction, has a error, heading error. So instead of going straight on a 0-degree angle, it moved on variable angle, which created that heading error that I showed in blue. So two problems. Two problems, these two problems need two controllers to fix them. So same system, two problems, two controllers. All right, so what could cause the moving on the curve problem? When, so more of the system. The wheels not moving at the same rate, right? They're not spinning the same. So the velocity of the wheel needs to be adjusted. So we need to control the velocity of the wheels, right? So that's one problem. So if we fix that, what do you expect to happen? You probably expect to see like, right? It was going straight, or from the beginning, it started just sweeping off, but still going straight, but the heading is not what you expected, right? So then needs another control to fix the heading. You fix it going on a curved line, goes straight. The heading error usually happens when you have, let's say this is autonomous robot, with autonomous robot, because the position control usually is based on the encoder of the wheel or based on the IMU you're using. So all are sensors. Sensors have error. It's accumulated error. So this is a very quick, like get off the path, was like 10 meter, 100 meter. So when you start any wheeled robot, they will have this built-in accumulation of error in them. So if it's not fixed, it will keep wearing off. We call it heading error. Now, there are ways to fix this. One, if this was outside, what would you suggest? How do we fix this error? What information we can use? You could use a sensor that sees those, right? Like LiDAR. So using a sensor that gives us another information to fix the current error. What else? GPS, you can get the coordinates. So you go 10 meters, check the coordinate and say, ah, I must be on N something, something on N something plus 1. Let's go back. So keep correcting itself, right? So that's the kind of controller you do for heading. So it's two different things. So I'm going to show you today the velocity control for the robot motor, because First of all, it happens all the time, happens inside, outside. It's easy to fix. The heading control is more difficult in terms of it's more complicated. You have to use maybe other controllers or other sensors to fix it. All right. Just to know that there will be two different kind of controller even for the same event that is happening here. So the goal is always, if this is error, this is time, we want to minimize or reduce our error. How do we get the function of error? Equal R minus Y. You get to that expression, you want to minimize that. You have done that before, right? So you can tell, you can plot that in MATLAB and see how is the behavior of your error function. You can, and if it is minimized, you can measure, it's like, okay, my control is performing well. So usually when you design controller, you want to look at the behavior of the error instead of the behavior of the system directly, because you're trying to minimize that error, right? All good so far? So we understand what we are trying to control. Now, there are different kind of controllers. In this course, we will work on 3 different approaches. One using PID control, which is a 3-term controller, PID. Then we can use root locus method, which is more of a visual way of doing things. We will use MATLAB for that. Then we are going to use compensators, lead and lag, which is a frequency response controller. The reason I chose these 3 is that, well, PID has a lot of application in a lot of industries. So everybody needs to know how PID controller works. How it works is easy. How to tune it is the part you need to practice more. The root locus is more of a design to give you ideas how pole and zero impact on response of a system. The lead lag compensator, you usually don't actually design lead or lag compensator, but because it looks at the frequency response, the body plot, gain and phase. So if you are looking at frequency response of your system, you're able to design a controller that will fix it. So you can design the controller in your frequency domain rather than time domain or S domain. All right. So we'll see how far we can get, but that's my goal, to walk you through all 3 methods. Now, PID controller, we have proportional, integral, and derivative. 3 different terms. They have coefficients. So those coefficients are where we get the names, or we represent those names with the coefficients. So KP, KI, KD. We reserve PI and D for PID controller. So try to be consistent. Don't say KR. Okay, because I wouldn't know what KR is. But I always know when I see KP is going to be something that relates to position. Do you remember in the error, when we're defining a static error constant, we had KP and KV and KA. KP was position error. This is the same thing. So proportional will be applied will apply again proportionally to the error of system. So all the examples we've seen so far that you had a gain of K, that's how proportional control works. It has a gain, there's nothing else in it, just sees the error and says, if your error is large, let's apply a value to it, and then to make it larger, and then let's run the system again and compensate for it. All right. We usually say KP is, if you think of a timeline, your proportional controller looks at the error right now. I'm moving 25 miles per hour. I'm supposed to go 30. I'm looking out, there's 5 difference. I'm seeing it right now. So I'm going to push the pedal proportionally and go fast. Right? So that's proportional controller. Now, your integral controller looks at the past, see how much error was accumulated. Now, with what gain I apply to those accumulated error to fix my current situation. Your derivative controller will say, okay, let's see the behavior of system. How can I predict the future and predict and compensate and will happen in the future. That's the derivative. So the derivative, if you think about it, if you think of this graph, the derivative is like the tangent of at that point of the system. So you can't tell what's the next point. You can predict. So you don't predict 10 hours in the future. You predict immediately in future what kind of error you're gonna get. You're gonna compensate for it. Then you go, okay, I'll compensate for like 90% of it. Then you see it is in the past now, right? So it goes to integral. See how much error you accumulated, and then you're at the present, you fix it to some proportional, and then keep going. So PID controller the art of designing a PID controller is to tune these three parameters, these three coefficients. It's on super easy. This is the control law. This is called control law. Control law. So control law is your UT. Remember, U is your control signal. So your control signal is made up of your KP, your proportional coefficient times the error of the system at that time. So proportionally, you are multiplying by error. Plus, so this is your proportional control. Plus your KI times the integral, the area under the curve before that point. So the accumulation of all the error in the past, right? So you're compensating for all those errors. So that's the I part plus D, KD times the derivative, which is the tangent, right? So the derivative tells you what will happen in the future or can estimate. So these are the three parameter of PID controller. That's it. That's the rule of PID controller. Up to this point is not difficult. Everybody can understand this. Now, what are those values? That's the problem, not the problem. That's the art. The art happens there, right? So when you're designing a controller, PID controller, the tuning of it is what takes time. Now, PID controller are usually tuned by error, trial and error. So zero scientific method. We can always come up with a good educated guess at the beginning, couple of trial and error, and find a good value for KI, KP, KB. Once you have better intuition, your educated guesses will be better, closer to what the final value is. Again, for the same problem, all 60 of you will come up with 60 different controllers, because you can't, like, if two people pick the same value for the PID controller, they might have had a coffee together and talked about, casually. Hey, I'm picking 10 and 0.1 and 1. What are you doing? Oh, I'm going for the same things. Let's submit that. That's how we know, like, who talked to who. And also, it does not help with your intuition, because the process helps with your intuition of designing controller. So there is one other term, U of B. So whenever you see U, it's input. Now, U of B is your bias term, your reset term, a term that you will add. You see that your control always behave and is lack of something constant. You can add that. It also could be that feed forward value we talked about. I need to go from 0 to where Brad is sitting. I don't know how far is that to tell my robot to go, but I know at least is 4 yards. 1, 2, 3, 4. That is the feed forward, right? I can measure where it is. From here, I'm going to keep measuring the error. 1.5 yards, 1 yard, 0.8 yard, whatever, and then I arrive. I'm reducing the error, right? So this part does the feedback, use feedback. The first part, I just said, oh, it's too far. I'm just gonna guess 4 yards to go. So that is the feed forward part. Sometimes it's cheaper to use that feed forward element. If you're doing that, it will show up here as a fixed constant. Because controller is the signal you're sending, right? They're sending a fixed amount, plus now see how close you're getting. All right. Now, these are all in time domain, right? Great. We don't like time domain, right? We do things in S domain because we want to use MATLAB and Simulink. That's why we like estimate. Otherwise, time domain is just fine. So you can convert them and write them in estimate. Do you remember how to convert a differential equation or equation time domain to estimate? That's why it is useful because now you should at least understand this. I don't want you to go from time to S here, but my system is G, right? My controller is D. Now, PID in terms of S domain, if you think of a box, you will see that there is KP plus KI over S plus KD times S. So this is a box. So this is a subsystem. There's actually a system inside this. So this will read the error, right? If I draw this, if I zoom in and I want to draw it here, let's say that's the box. So there's error and there is U, which is the controller output. How do I build this block diagram that is equal to what's in the box? Are they in series? Are they in parallel? Two of them in series, one of them in parallel. How do you think these blocks have to be arranged? What's that? Parallel. Parallel, okay. So how many lines do I need? How many branches? 3, 2, 3. 3, the more the better. 3. So 1, 2, 3. So why do you say 3? Blocks being added to each other, right? Parallel. So I need 3. And I know what goes in each. The first one is just a KP. That's the block. By the way, that's how you build your block diagram when you go to Simulink on Friday. You should be able to do these. Then the next one is KI over S. Do you remember 1 over S? What was that? Step is an integrator action. So a step is a form that we can write as 1 over S. But 1 over S is your integrator, if you remember. So I can say this is Ki times, if it's in series, we can multiply, right? It's give the same thing. You could also say Ki over S. It's just the same thing. It's a gain that is multiplied. I'm doing it the way that you would do in Simulink, all the blocks separately. Last one, KD times S. So this is KD times, I have to put in series, S. So a block that has S in it is called differentiator. Integrator differentiator, that's our PID controller. Now, 1 over S is a pole at 0 origin. S is a 0 at 0 origin. So these two, they're placing it on top of each other, but because of different Ki and Kp, the impact on the system will be different. All right? So this is how you show your PID controller in Simulink, in S domain. There are 2 ways to do it. When we get to Simulink, you can use PID control module, or you could build them separately. Yes.
How would you add like a bias and would you add a 4th branch?
What do you add? Yeah, bias them depending on what it is. If it was just a gain value, you just add that as another parallel gain. But if it has an equation in it, you had to build the equation. And we already practiced how to go from equation to block diagram, right? That's why we talked about it before now. All right, so that is your controller. This is your system. So control applied to system. That also is the loop of your gain, the gain of the loop gain, sorry. So from there, in Simulink, you just hit run, it plots the response for you. It's so easy that we want to use Simulink, all right? But the only thing Simulink does is does the calculation for you, the part that you're doing by hand. Everything else, you have to do it. So if you build this wrong or set the conditions wrong, you won't get the correct answer. It also doesn't interpret it for you. You have to do it. It doesn't change the K values for you. Well, it does, but not always correctly. You are the final step in this process. All right, so it's not human out of the loop, it's human in the loop process. Any questions so far? Sorry, give me that. No? Okay, so let's go back to our motor controller in Volley Robot. So our motor controller, let's say that, well, we know, let's just focus on the velocity control. Instead of going on a curve, we want to make sure it goes on a straight line. Now, when you have an open loop system, you just have the motor, right? And usually your desired value is a velocity. The motor doesn't understand velocity. The motor understands voltage or current, right? So you have to convert that velocity to voltage. Usually comes with the motor driver. So you just connect and it's good. It takes velocity or angle from you or RPM and it spits out that. So this whole thing happens inside. Thankfully, you don't have to do it. But this is what happens inside your motor driver. But if you don't read the actual value, it's an open loop system. You don't necessarily get what you desire. Now, if we close the loop, now here, this adjusted voltage is this guy. It just means that whatever comes out of your control will be adjusted to become something that the motor understands, say voltage, all right? So there's a difference. Whatever your controller spits out is not exactly the same thing your plant or your system is going to use. Depending if the units were different, something has to happen to convert. Usually it is done on the plant side, all right? Now, let's say that we added the feedback control, right? If the feedback line as well, so we close the loop and then we give it a step input, right? The red line is at 1, is a step input. The response of a system is in blue line. Is this a good response? No. What's the major problem here? We need to know the major problem to be able to design the controller. What's the major problem?
I would say like,
It's what?
not getting the whole.
So can you tell me in terms of controller, that things that we learned?
So like,
So you wanted to go to the red line, you're at the blue line, right? So, like you want to be here, you're here. What's the problem? What do you have that you don't like? A big error, right? Steady state error, which also stays the SS error. But where is it? Here. So after some settling time, after some time passed, then we see that we have that error because here we don't care. The system is still settling down. So we need to find that settling time and then find a steady state error. So two things that we need to watch when we are designing your controller, right? Now, both of them can improve, but the first one is the steady state error. We want to get rid of that. So do you remember from our other class, other lectures, like how can we get rid of the steady state error? What did we do before in the last, I think, example we did? It was in MATLAB. I just showed you the MATLAB. What did I do? Funny what? You remember something, but it was the other one. The damper was fixed after we did the other one. You remember how did we get rid of this? There was a series error between two ramps, right? I did something, they were on top of each other. There was some oscillation. We said that we should improve the damping to get rid of it. What was the thing we did? The other what? The pole? So it wasn't a specific one, right? At the origin, what do we call them? We added an integrator, right? 1 over x. So in PID controller, what term is related to integration? The integrator part, the I, right? So we know that our controller has to have I in it to be able to get rid of that steady state error. This is really important because designing a PID all 3 terms is expensive because you have to tune all 3 of them. It takes more time and it impacts the component of your system. Literally, you have to buy a more expensive motor to be able to like run the system based on your controller, right? So you have to pick the exact one that fixes the problem for you. So one is that we know you have to get rid of the error. Now, the thing is, you can't just have I controller. The simple controller that we can have is a P controller, proportional. It's just a gain. Gain of one is still a gain, right? It's just one. So PI becomes a controller. So we know that we have to first try a PI controller by adjusting our KI value, see how much we can get rid of that error. Now, if we add I controller, we know we might have some oscillation. We saw that before, right? Now, to get rid of oscillation, we can adjust our key, or if we couldn't, we have to add the derivative, which has the damping. So if you couldn't use P and I together to get rid of the problem, you add P. So controllers, the subset of PID controller are PI controller, PD controller, and PID controller, or P controller. Sometimes it's just a game, and we solve some of the errors, some of the problems with just P controller. So if we only add a proportional control, if you draw that, if you had a transfer function, you will see that it compensates. Like if you had a big error, the first thing you do, you just add P. It just means your system doesn't have enough juice. Just give it some gain value and then just bring everything up. It would bring your error to a smaller value. The other impact is it makes it faster. So faster rise time doesn't say anything about stellar time though. It would create overshoot if your P is big, meaning that you're giving more juice, so the system like whoop, and then but that whoop might be an overshoot because the system is running faster, bigger power. You might have a steady state offset, some error. So changing P on its own, you might not get rid of your steady state error. You might be some that. To fix that, you add the I. The I will get rid of that your remaining error. So every time you have I in your controller, it is guaranteed you're not going to have a steady state error because you're adding the pole at the origin 1S integrated system. So, which is the third one, proportional integral, PI. The integral term eliminates the accumulated error, but increases overshoot can add oscillation to your system. That's expected. Now, when you see that, you have to either go back to P, change the P value, adjust it, or you might have to add a D component. Now, sometimes you will use proportional derivative. Sometimes you go with P, and then you see, oh, I have a big overshoot. D acts as damping, right? So if you add a little damping to your system, you might get rid of that overshoot. And if you play with them, sometimes P is good enough for getting rid of the steady state error. So the solution could be a PD controller, not a PI controller. So who knows which one it is? I don't know. You will try. You will build your intuition. You will give it a try on all of them, and you find something. Now someone says, you know what, I'm just going to do this PID controller, change all three of them, put in MATLAB, it has a toolbox, it gives me a number. Great. Now go buy the component. It impacts your power consumption, the motor that you have to choose. You might have to even, I don't know, add a sensor that will read the error to some great resolution. But that resolution that can actually, the error can do something meaningful. So you can't just say, on the paper, everything looks great. It doesn't mean anything. All right. The controller has direct impact of the component that you're going to choose for your system. But we will learn all of that. All right. So this is just to tell you that if it worked on the paper, it doesn't mean that's a good controller. It has to look good on the paper, but it doesn't mean if it is a good controller. All right. Now, if you add all of them, it becomes PID controller. So when I say P controller, my control law is only KP times ET. That's what it means. If I say PD would be, U would be KP times error plus D was derivative. So KD times D ET DT. Now, how do I calculate DET dt when I'm solving a problem on MATLAB myself, like I'm writing the code? You would discretize. You say from time, because when you create a time vector, you basically have the function value at every time, right? So time k plus 1 minus time k divided by the difference time is the error in that zero thing. So this is where discretization comes in. You don't have to discretize as much, because when you create vectors for time, you will have a vector for the function value, the same length of your time vector. So MATLAB will do the rest for you. We won't do these by hand. That's why MATLAB was needed up to this stage. So this is a PID controller applied to the robot ball e-motor system. And you see that the velocity had to be 1. It picked up when overshoot, but then after some time, we have our desired velocity. For whoever tuned this time of 1 and 1.8, whatever this was good enough, was fast enough. So you didn't have to push back the settling time, right? This is TRS. So this is also important, because if TRS is supposed to be fast, your motor has to be fast and it can break, so it has to be a stronger motor, more expensive. This is a $50, this is $500. So the first graph that we saw, trajectory is position. If you think about the trajectory of robot, instead of going on a straight line, it went on a curved line, right? If you would look at the velocity of each wheel, you would see that there will be a difference. If the blue one is left motor, it means left motor is spinning faster. One motor is spinning faster means that you will turn to that direction, right? So you expect a left turn. Here we have a left turn. So change of velocity impacts in position, because what we see is the position of the robot, right? But what was wrong was in the velocity that we need to control it. Now, if you control that velocity and becomes after that PID controller, you see blue and green are on top of each other, so they are the same velocity, your robot goes on a straight line. So we fixed the curve problem. So one controller did its job. Now control number 2, what should it do? Fix the heading, right? That requires another set of controller. And this is not what we will discuss here. You just, because it would be actually more advanced, but a system could have multiple interlock controllers. So if you wanted this controller to control heading and velocity, you have to create a cascaded controller, which would have its own Ki, Kp, and Kd. So there will be 2 sets of PID values. They could all be PID type controller, all right? Now, your class participation, I'm gonna help you with this. I will read this, I will explain what to do, but I want you to do it and submit whatever you have, okay? So the question says, what is the resulting output from the PID controller? So PID output, when the cross-track error is a constant of 3. So this is your cross-track error. If you look, you have position and time. So your actual position and target. The target position or desired position was supposed to be here. Your actual position is here. What's the error? The error is in between them and it's 3, right? But the error is 3 across the whole 5 seconds of it. So 4, and this has been for the last 5 seconds. So T is 5, your E is 3, 4, 0, 4, 1, 4, 2, 4, 3 to 5. They're all the same amount of error. You have Ki, Kp, Kd values. What does output of PID controller mean? What am I looking for? Do you remember control law U, right? U of T, now T for 5 seconds. So I'm looking for U of 5. what happens, like what should be the output of this controller after 5 seconds that can fix this problem. So you're coming up with a PID controller control law using this value. It will give you a number if you put all these values in. I will write the control law here for you. This is your controller. I want the output of this for the situation that you have. I'm going to pause the recording.